You've been flying straight and level for 2 hours. Your NDB bearing is rock steady in the pitch-black sky. Then, without warning, the ADF needle starts wildly sweeping left and right. The air outside is smooth, there is no mechanical failure, and the ground transmitter is broadcasting normally. The only variable that shifted is that the sun went down. High above you, the ionosphere just switched off a specific layer of ionized gas. That single atmospheric shift is all it takes to render the NDB completely useless. Operational safety requires knowing the invisible physics dictating your instruments. Rote memorization of dials will not save you when the atmosphere changes the rules of propagation. Radio waves leaving a transmitter do not travel the same way. Their exact physical geometry is dictated entirely by their frequency, breaking down into 3 distinct paths. This wireframe shows the first path, the ground wave. It literally hugs the Earth's surface, curving smoothly to track the exact curvature of the terrain. This terrain-following behavior makes it highly reliable over short distances. It is the primary propagation method used by low-frequency and medium-frequency navaids, like the NDB. The second path is the skywave. Instead of following the ground, it travels straight up, strikes a dense layer of the atmosphere, and reflects sharply back down to the surface hundreds of miles away. Because it bounces high above the Earth, it offers massive global range. High-frequency communications rely on it. But that reflection is inherently unstable and highly unpredictable. That exact unpredictability is the physical mechanism behind the NDB night effect. Finally, we have the space wave. This signal travels in a strict, unbending line straight from the antenna, piercing the atmosphere and continuing out into space. It strictly ignores the curvature of the Earth and refuses to bounce off atmospheric layers. It requires a direct, unobstructed line of sight from the transmitter to the aircraft receiver. The frequency of your instrument forces the wave into one of these exact geometric paths, which in turn defines its operational limits in the cockpit. Knowing which instrument produces which wave type requires mapping the frequency spectrum. Looking at this frequency table, we start at the lower end, the low and medium frequency bands, spanning from 30 kHz up to 3 MHz. These frequencies generate both ground and sky waves. This is the operational domain of the NDB. Moving up the spectrum, we reach the very high frequency, or VHF band, occupying the space from 30 to 300 MHz. At this exact threshold, waves no longer bend or bounce. VHF generates strictly space waves, powering line-of-sight tools like the VOR, the ILS localizer, and your primary voice communications. The highest bands tested are ultra-high and super-high frequency, covering everything above 300 MHz. These are also strictly line-of-sight space waves. This band handles precision equipment like DME, GPS, secondary surveillance radar, and weather radar. For the DGCA exam, you must remember this strict boundary rule. Everything operating at VHF and above is strictly line of sight. They are structurally incapable of bending around the Earth. To understand why the NDB fails at night, we have to look closely at the ionosphere, a volatile layer of ionized gas sitting between 60 and 1,000 kilometers above the surface. This gas is not uniform. It stratifies into distinct altitude blocks, the D, E, and F layers. Here is the atmospheric cross-section during the day. Solar radiation intensely ionizes the lowest level, creating a thick D layer. Notice how an LF or MF skywave from the ground transmitter strikes it and dissolves entirely. During daylight hours, the D layer acts as an impenetrable shield. It absorbs low and medium frequency skywaves before they can bounce. Because the skywave is effectively killed by the D layer, only the stable, terrain-following ground wave successfully reaches the ADF antenna on your aircraft. But when the sun goes down, solar radiation stops. The low-altitude D layer completely dissipates. Without the D layer blocking the path, the signal reaches the much higher F layer. This layer remains highly ionized at night and acts as a massive radio mirror. The rogue skywave shoots straight through where the D layer used to be, strikes the F layer, and violently bounces back to Earth, hitting the aircraft at the exact same time as the ground wave. 2 signals from the same NDB are now hitting the receiver from different angles and at slightly different times. This mixing of the ground wave and the returning skywave is the exact physical mechanism causing the ADF needle to wildly oscillate. Think about the physics for a second. Day or night, when is the NDB bearing actually reliable? day. Because the sun maintains the D-layer shield, the night effect is not a random electronic glitch. It is a predictable, mechanical failure caused by the total loss of an atmospheric shield. Stepping away from the ionosphere, let's look at the frequencies that ignore atmospheric layers entirely, VHF space waves. Remember, they travel in perfectly straight lines. This diagram shows how straight-line travel forces a strict cutoff. The signal cannot follow the curve of the Earth. Instead, the range is blocked by the horizon. Atmospheric refraction bends the signal just a fraction, pushing the radio horizon roughly 15% further than the visual optical horizon. Because this is a strict geometric boundary, it can be mathematically defined. The DGCA tests this exact formula. Maximum range in nautical miles equals 1.25 times the square root of the aircraft's height in feet. If you are flying at 10,000 feet, the square root is 100. Multiply that by 1.25, and you hit a hard physical reception limit of 125 nautical miles. Drop down to 3,600 feet. The square root is 60. Multiply by 1.25, and your maximum range drops to just 75 nautical miles. VHF range is an absolute mathematical boundary, dictated strictly by the geometry of your altitude. It has absolutely nothing to do with the power output of the transmitter on the ground. While these geometric rules govern standard operations, the atmosphere is inherently chaotic. Certain meteorological conditions create edge cases where the normal rules of propagation break down. The first anomaly is fading, a condition that frequently degrades NDB signals at medium ranges. Looking at these wave patterns, fading occurs when a ground wave and a returning sky wave arrive slightly out of phase. They directly interfere with one another, causing the signal strength in your headset to rapidly fluctuate or cancel out entirely. The second anomaly is ducting, which targets VHS and UHF space waves. Watch how the wave interacts with these temperature inversion layers. The VHF signal gets trapped, bouncing between anomalous temperature bands, funneling the wave far beyond its normal line-of-sight range. This is often the culprit behind unexpected false radar returns. To summarize the facts, ground waves power the NDB, HF sky waves reflect off the F layer, and when the D layer disappears at night, that reflection causes the night effect. Everything operating at VHF and above is strict line of sight, bounded by the radio horizon formula of 1.25 times the square root of your height in feet. Remember, radio physics dictate exactly what your instruments can see, and exactly when they will lie to you. Next time, we explore how those exact same principles govern primary and secondary radar, and how ATC tracks your specific position in the sky.